Hi everyone. So in this video we'll be discussing Maxout hidden layer activation functions. So this is a variant of ReLU where one unit or one activation function can be connected to multiple weights coming from the last layer, right? And then it takes the maximum out of these values, right? So maybe here I have one function connected to 3 units and then it takes the maximum out of them. Now you can think of ReLU as actually a Maxout unit with 2 inputs. One input is fixed to 0 and the other input is coming from the unit itself, from the linear transformation through the unit, right? So that's why we consider it as a variant of ReLU. So also that tells you that we can set any of these inputs to max out to a fixed value, right? So it doesn't have to be a value coming from the unit before, or you can think of as setting that weight of the input to 0, right? So what it does is basically, so think of this figure like you have 3 curves, red, blue, and green. So it takes the maximum of them. So this is the black highlighting, right? So a more accurate representation is actually because all of these inputs are linear transformations. So it does look like this. So you have here blue, green, and red lines. So it does look like a piecewise linear function, meaning from here to here, it's a linear function. From here to here, it's a linear function. From here to here, it's a linear function. So it does implement piecewise linear functions. As the number of inputs increases, it can approximate actually any continuous function with a small error. So if we make these pieces very small, then we can approximate through the Maxout any continuous function. So this is a very powerful activation function because I can have an arbitrarily large layer before it, and then through the Maxout I can approximate any continuous function. So that's very complex learning, right? But of course there is a cost, because when you increase the number of parameters, this is a very complex hypothesis space, right? So as you increase k, you increase the size of the layer before the Maxout. So remember, for every Maxout unit you will have a number of parameters k. That number has to be very large to approximate a continuous function with a small error. Right, so it can add a lot of complexity using Maxout, but it can also be very powerful for learning. So so now there are 2 variants or 2 design options for Maxout functions. You could either do clustering, where you group the units of the last layer into groups, and then each group of k units you input them into a Maxout function. And the advantage of this is that you actually reduce the layer dimensionality. So if k equals 3 and you do this clustering, then you reduce the size of the layer by 3, right? So if your layer had 3000 units, then after Maxout it becomes only 1000, right? So it does reduce the dimensionality, and hence it reduces the number of parameters going to the next layer. Another option is, and you could always have a mix of these 2 options. Another option is to have overlap, meaning that one unit in the layer before Maxout can be connected to more than one Maxout unit, right? So that adds redundancy between the Maxout units, and this can be something that's very useful. For example, later when we'll discuss dropout, if you're doing clustering and then you drop out one of the Maxout units, then you completely lost that part of the network. So that part of the network is not learning anymore. But here with this overlap, you guarantee that when you do dropout for few of the Maxout units, still all of the units are connected to at least one present Maxout unit. Right, and we'll come back to that later when we discuss dropout in detail. Now this overlap structure can add robustness and can prevent what's called catastrophic forgetting. And catastrophic forgetting is simply a phenomena that refers to permanently forgetting something that was learned during training. So maybe in the 10th iteration, there is some concept that we learned. Some of these units have learned to detect a certain feature, and then by iteration 20, we completely forgot that information permanently. So this is called catastrophic forgetting. Now this overlap structure with Maxout can help, like empirically it was found to help prevent catastrophic forgetting for an obvious reason, is that there is redundancy between these units, right? So the learned information is not concentrated in few of the units. But of course, the cost is a more complex hypothesis space, right? So here actually it's not necessarily the case that the number of Maxout units will be less than the number of units in the layer before. It can be slightly less, it can be even more, right? So we lose the advantage of the aggressive reduction in dimensionality of the layer that we get through clustering. So this is a very interesting activation function that are used in a wide range of applications, but its design is tricky, right? So you have to choose, like there is a lot of design choices that you make through Maxout units, right? How many parameters will be input to the unit, and how the connectivity will work between the units of the last layer and the Maxout units. Thank you.